Okay, here are the last two problems for the FRQs. Sample test number 2. Here is number 4. I know it's a little bit. Here's number 4, parts A, B, C, and D. We're dealing with differential equations and slope fields. So let's go ahead and take a look at part A. So we know from the original prompt that we have dy dx is equal to, we have an x in the denominator. I know we have a y squared up top. It's y minus y squared up top. And it's saying, confirm that this function here is a general solution for this given differential equation. One way that you can confirm a solution is by working backwards, because if we take the derivative of y, we should get dy dx. In other words, we're going to take the derivative of this function here, and we're going to make sure that we get that derivative. Well, let's see what happens. If we have y equals x over the quantity x plus c, and c is a constant, we take derivative both sides, and on the right side, or left side, we get dy dx. So the left side is just fine. The right side is going to be a quotient rule. We have a high and low function, and our derivative is going to be low d high minus high d low over low low. That's what we get. Well, first, the bottom is x plus c, so that's all of a sudden going to become x plus c and then the quantity squared. And then on top, we're going to have low d high, so that's going to be x plus c, the low, times the derivative of the high, which is just 1. And then minus high d low. Well, the high is originally x times the derivative of the bottom. Well, c is a constant, so that goes to 0. The derivative of x is just 1. So now as I'm looking at this, and if I were to simplify it, that is x plus c, or x plus c minus x. So that's just going to be c over x plus c quantity squared. And you're asking yourself, probably at this point, how does this equal y minus y squared over x? Well, let's see what we would get if we have y minus y squared over x. Y minus y squared over x is going to be x over x plus c minus x squared over x plus c quantity squared all over x. Now, if I'm looking at this and I'm trying to ask myself, how would I start to simplify this? I would probably first, you would think you'd want to get common denominators, but I think I can get rid of this denominator even faster. And again, how did I come up with it? How did he come up with that? This is y squared. It's y minus y squared all over x. So I'm trying to see if that somehow translates into this piece that I got here. If I multiply, we have x over x plus c minus x squared over x plus c quantity squared. I'll multiply that whole thing by 1 over x. That gives me, as x distributes and it reduces with both each the first and the second term, so that's going to be 1 minus x, and the first one is over x plus c, and the second one is over x plus c quantity squared. Well, if I wanted to make this a common denominator, I need to multiply this left one by x plus c over x plus c. That's going to give me x plus c quantity squared on the bottom. And on the top, I'll have x plus c minus x, or just c. Hey, it's the same thing. So this is equal to this if I replace the y with the original function. Okay, so check. That's true that those things work. If we take the derivative of this piece, let's use my pointer. If we take the derivative of this piece, that means that we get this up here. Then it asks us to also confirm something else. I work all over the place, but it asks us to state that somehow or show that the solutions contain 0, 0. That just means that x equals 0 and y equals 0, and that that's going to somehow be always true. Well, if we know that y equals x over x plus c is the original function, we replace x and y with 0 and 0. That's going to be 0 equals 0 over 0 plus c. 0 equals 0. 0 equals 0 no matter what. That's true. If this balances out where both sides equal 0, and this bottom is always going to have a plus c at least in it, there's not going to be a denominator of 0, then we will always be true. So all solutions do contain 0, 0. Let's look at part B. Part B says write an equation of the particular solution that contains a point 1, 2 and find the value of dy dx at 0, 0 for this solution. Okay, well, if we're trying to do this, we have two things going on. We're finding the original equation and we're finding dy dx. And what's happening in each of these is that x equals 1 and y equals 2. Well, the original equation said y equals x over x plus c. What it's asking us to do then is solve for c. And we know x and y then, because we have those given to us for this particular solution. Y is 2, x is 1, so I'm going to replace those. Then if I multiply both sides by this denominator, or there's other ways to do it too, I can just flip both sides. That would give me 1/2 equals 1 plus c. And when I subtract 1, that's really subtracting 2 over 2, so I get negative 1/2 equals c. I know I did some pretty quick algebra there, but that means in this original equation that negative 1/2 equals c. That tells me that y equals x over x minus 1/2. Then if I'm trying to find dy dx, dy dx had y minus y squared over x. Again, I'm just going to replace x with 1 and y with 2. That tells me that I have 2 minus 2 squared over 1, which is actually pretty easy. That's just 2 minus 4 over 1, or negative 2. So that's my slope. That was pretty fast. Part B was easy, way easier than Part A, or at least less work. Part C, write an equation of the vertical and horizontal asymptotes of the particular solution found in B. Well, vertical and horizontal asymptotes are two different things. If we're looking for horizontal asymptotes, that's the limit as x goes to infinity, and also the limit as x goes to negative infinity. So we're looking in the limit as x goes to infinity of x over x plus c, and then also of x over x plus c as we go to negative infinity. Well, these are actually equal to each other, because if I see what's happening here, if I just multiply everything by 1 over x on top and bottom, then I get 1 over 1 plus c over x. Similarly for the other one, if I multiply the top and bottom by 1 over x and 1 over x, as x goes to infinity, I'll get 1 over 1 plus c over x. That tells me this little piece right here, as x goes to infinity, that's going to become so small that it equals 0. Similarly to this piece here, it's going to become so small that it equals 0. And that means that the limit as x approaches infinity, or the limit as x approaches negative infinity, is equal to 1. So my horizontal asymptote is equal to 1. Vertical is when the denominator equals 0 and the numerator is something non-zero. So let's see when that would happen. The vertical asymptote would be, we have y equals x over x plus c. So we're really looking for this denominator part here to equal 0. When does x plus c equal 0? When x equals negative c. So that's my vertical asymptote. Pretty easy there. So we have a horizontal asymptote at 1. That's our y value. And we have a vertical asymptote at x equals negative c. Do we have more for this problem? The slope field for the given differential equation is provided. Sketch both branches of the particular solution curve that passes through the point 1, 2. So I'm looking at this point right here, 1, 2. Now, to sketch this curve, I'll go ahead and sketch it in green just to do something different. Whenever you're trying to sketch a differential equation curve, all you got to do is make sure that you follow these lines. Now it looks like I'm going to have a vertical asymptote at 0. Is that what's happening there? My horizontal asymptote, as I figured out early, was at 1. Similarly on the other side, it's also going to be at 1. So that means that I need to have this type of equation here. Why do I know it's not going to be on the bottom? Because my horizontal asymptote should be going here. Actually, you know what? The horizontal asymptote could be on the other side. So that means that this curve could be here. Kind of weird to think about how these curves grow. But there's a lot of different things you can see. It depends on really where you start. This one for sure happens. So all you do is you extend those branches out. And I would actually think that it does go up top. You guys are saying, Mr. Butler, why do you keep changing your mind? Because this is how I think it goes. We're going to start here, go up to those, and flatten out. There. Alright, let's look at the next problem. Consider the relation defined by the equation tangent y equals x plus y in the open interval negative 2 pi to 2 pi. It says find dy dx. This is pretty straightforward. It's just doing implicit differentiation. So when it says right here find dy dx in terms of y, we got tangent y equals x plus y. So tangent y equals x plus y. We need to take the derivative of both sides. The derivative of tangent is really secant squared, so it's going to be secant squared y times dy dx. Why did I have to put that in there? Because I took the derivative of y. Now for this next one I have two terms. When I take the derivative of x, that's just 1. When I take the derivative of y, that's 1, but I also got to multiply by dy dx, that chain rule happening because I have the dy dx's. Now if I look at this, to simplify it here, I'm going to have secant squared y dy dx. And if I move this term over to the other side, it's going to be minus 1, or dy dx times 1, and that equals 1. Then when I factor out that dy dx, we're going to have dy dx equals, well, times, pardon me, we're just factoring it out, secant squared y minus 1 equals 1. Now just to continue the algebra over here, we can divide both sides by secant squared y minus 1, secant squared y minus 1. That means that we're going to get dy dx equals 1 over secant squared y minus 1. Well, that wasn't too bad. That's actually a trig identity. We don't need to change it, but we could change it if we wanted to. Find the x and y coordinate of each point where the tangent line of the graph is vertical. Okay, well that's kind of interesting here. That's asking us to figure out when is the tangent line vertical. For a vertical tangent line, that means that we have some type of number over 0 for any type of vertical line. Vertical really implies that we have a ratio where the numerator has a number but the bottom is becoming 0. Well, for that to happen, we know that our slope dy dx is equal to 1 over secant squared y minus 1. So we're really looking for when this denominator is equal to 0. Well, let's set that equal to 0. Secant squared y minus 1 is equal to 0. When does secant squared y equal 1? We can even square root both sides. That means that secant of y equals 1. Another way of looking at that, that's the same thing as 1 over cosine y equals 1. So when does cosine y equal 1? We got a lot of algebra going on here. That means that arc cosine of 1 we could do to both sides, but really just use our knowledge of the trig unit circle. That means that y is going to be equal to, we know that we go from, what was our range again? Let's double check that. Our range in the original prompt says we go from negative 2 pi to 2 pi. So we hit 0 in the middle, but we don't go all the way to 2 pi, and we don't go all the way to negative 2 pi. So the only place that really happens then is going to be y equals 0. But now here's something interesting. It said find the x and y coordinate point. Well, if y equals 0 works, I need to figure out what x would be. Well, the original function is tangent of y equals x plus y. So let's use that to help us find x. We know that tangent, let's do a different color here. How about blue? Tangent y equals x plus y. We know y equals 1, so tangent of 1 equals x plus 1. So x is going to be tangent of 1 minus 1. Equals x. Ooh, I just noticed something here. Let's go ahead and mix that. Tangent of 1 minus 1 equals x. Make that blue. What I notice is right here. When I take the square root of 1, that's actually plus or minus 1. So when does cosine of y equal plus or minus 1? And it's at 0 and pi. So tangent of 1 minus 1 equals x. So we have this first point that we're looking at, and that's when y equals 1. And x is tangent of 1 minus 1. Well, let's see what happens if we plugged in pi. That would mean that tangent of pi is equal to x plus pi. And tangent of pi, that's sine over cosine, sine of pi equals 0. So 0 equals x plus pi. That means that x equals negative pi. Okay. So if x equals negative pi when y equals pi, the other place where we have a vertical tangent is when we have negative pi here and pi for our y. So here's our vertical tangents. Our vertical, what did they call them? Vertical segments? Yeah, vertical tangents. Clean that up a little bit. There we go. All right, let's look at the next section. It says find the second derivative. Well, we know that 1 over secant squared y minus 1 equals dy dx. So I'm going to do a little bit of trig substitution here to simplify this denominator, make it a little bit easier to take the second derivative. I know that starting with Pythagorean identity, sine squared y plus cosine squared y equals 1. And if I divide each of these by cosine squared y. Let's see what I would get. That means I'd have tangent squared y plus 1 equals secant squared y. So if I subtract this 1 over there, that means that tangent squared y equals secant squared y minus 1. That really means that dy dx is equal to 1 over tangent squared y. Another way of thinking of that is this is equal to cotangent squared y. This is almost too easy. Because when we take the derivative of cotangent squared y, we got to take the derivative of both sides of this. That means that we're going to get d squared y dx squared on this side. And on the right side, it's just the derivative of cotangent squared y. The derivative of tangent is secant squared. The derivative of cotangent is negative cosecant squared y. But then we got to multiply it by dy dx. So we're going to fill in that original first derivative that we had there. So it means we have negative cosecant squared y. Cosecant squared y. Let's take that back a little bit, clean it up. Negative cosecant squared y. And the original function was cotangent squared y. There we go. Let's see if there's a part D. Oh, we're moving on to number 6, and we are almost done, so close to the end here. The figure above shows a graph of f primed. That's key in interpreting all this data here. The derivative of f. The domain is negative 4 to 4. Okay. The derivative of f is even. That sounds fun. They actually underlined that. That must be important. That means that f of negative 3 equals f of 3, which equals 0. So right here, this is at negative 3, and right here, this is at 3. For what value of x in the interval does f have a relative maximum? Justify your answer. Well, let's take a look at that. First, maybe we should take a picture of this graph. Oops, take that piece down. Move this down a little bit. For what value of x does it have a relative maximum? That's very key to know. What we're looking at right here is actually the derivative. To find a relative max, we know that we have a max when before we were increasing and afterwards we are decreasing, meaning that f prime is greater than 0 before and f prime is less than 0 after. So f prime is going to change sign from positive to negative. When does that happen? It doesn't happen here. It's 0 here, but it goes from negative to positive. It does happen, however, on the other side when it goes from positive to negative. So f of 3 is a max because f prime of x changes sign from positive to negative, which really means that f changes from increasing to decreasing. There we go. Next, part B. When does it have a relative min? Well, that's actually the inverse of what we were just saying. We had said that it was a maximum because it changed from positive to negative. So remember over here, when it hits 0 at x equals negative 3. So for what value of x at x equals negative 3, f has a relative min because f prime of x changes sign from negative to positive, which really means that f of x changes from decreasing to increasing. Let's look at part C. Part C, for what values of x is the graph of f concave down? Use f prime to justify your answer. For f to be concave down, that means that f double prime of x has to be negative. Well, how do we know that f double prime of x is negative? That means that f prime of x is decreasing. Well, if f double prime of x is negative, that means that f prime of x is decreasing. So we look at it, and let's look at the original equation here. When is it decreasing? I'm going to go ahead and color that in red. From negative 2 to 0, and from 2, it said the domain was 4, so it goes all the way down to here. So these two red zones, that's going to be where it's concave down. So for x is between negative 2 and 0, and x is between 2 and 4 was the other interval. The original function is concave down because f prime of x is decreasing. There you go. If f of 0 equals 0, find the value of negative a to a of f of x dx. Well, assuming a is between negative 4 and 4, because that's our domain. We can't really go outside that domain, otherwise we couldn't do this. Well, if f of 0 equals 0, let's go ahead and take a picture of our original function here. Do that again. Okay. If f of 0 equals 0, that means that this area here, this negative area plus this positive area, in other words, our initial value equals 0. That's our constant. Well, if we're looking at these two areas, from negative a to a, that means that it would be 2 times the integral from 0 to a of f of x. Because it's even. How do we know that? Because we're looking at this going from negative a to a. Like, for example, if I went from negative 2 to 2, this is balanced on the left side and the right side. In other words, the green and the red are the exact same. So it's just going to be equal to 2 times the integral from 0 to a of f of x. I don't know if they're looking for something else. I don't see it really possible to find exact values otherwise. We don't know the actual function here. So we can't do much more than that. So justify our answer. How do we justify that? It's because the function is even. well, we can probably do more than that because we're not looking for this area. We're looking for the area of f of x. Let's go look back at our original information. We know that f of negative 3 equals 3, which equals 0 for f prime. We know that this is the derivative. So if I were to kind of sketch the original function, that means I'm going down, I hit a point, and then I'm going back up, and then increase a lot, not so much anymore, and I increase even more, and then I'm going to come back down. So this is actually a function that's odd. The function f prime of x is even, but then f of x is going to be odd. That means that the integral from negative a to a of f of x is 0. For example, let's say that we had an even function, or as our derivative, let's say that f prime of x equals x to the fourth, some c times x to the fourth. Well, then that means that f of x, the antiderivative of that, would equal c times x to the fifth over 5 plus c. But c equals 0 because f of 0 equals 0. That means that this is an odd function, and that the odd function, the area of an odd function, is always going to be the same on the left as it is on the right. And this negative side is going to cancel out the positive side. That's a little bit different than I was expecting. So the answer is it would equal 0 because it's odd. Thank you and have a good night.